Morning, everyone, and welcome to day 2 of the SPDK, PMDK, and vTune Summit. My name is Seth Howell. I'm a cloud software engineer at Intel, and I'm here with Ziye. We are, yeah, we both work at Intel on the SPDK team. Today we're here to talk to you not about birds or planes, but the SPDK NVMe over Fabrics target and initiator. And while we never hope that you mistake our software for something with wings, it really does make I/O fly through user space and into your storage devices. So I'm going to get us started off today with a little introduction of how the SPDK NVMe over Fabrics target initiator came to be, and give you sort of a state of the transport on RDMA, some of the things that we've already added to improve performance and memory efficiency, and some things that are coming. Then Ziye is going to come in and give an introduction to the brand new TCP transport that we're really excited about. So the NVMe over Fabrics spec was released in May of 2016, and just 2 months later, SPDK released its NVMe over Fabrics target with an RDMA transport. Over the next year, we did a lot of functional hardening and integration testing with the kernel initiator. We continue to make improvements throughout 2018, and in January of this year, we released the TCP transport target. The host timeline is pretty similar. About 6 months after the target was released, we released the host or the initiator side for SPDK, and did a lot of interoperability testing with the kernel, continued to improve it. The TCP initiator was released at the same time as the TCP target in January of this year, and we're working in 1904 and beyond. We're working to continue the performance that you all expect to see from the NVMe over Fabrics target initiator. So I just want to get into a little bit of the design decisions that were made when creating the initial NVMe over Fabrics target. If you're familiar with SPDK but not as familiar with the SPDK or the NVMe over Fabrics target, the best way to describe it is it feels exactly like how you would expect SPDK to feel. And most of that is due to the fact that we are built right on top of the SPDK pulled mode NVMe driver. So a lot of those design considerations that went into the pulled mode driver continue to influence the NVMe over Fabrics target. So one of the biggest things is polling per core. So for example, on the NVMe driver, we have one queue pair per core that we submit I/O to. And so in a similar fashion, all of the connections on a single core are pulled at the same time, and completions are generated for those as we poll. As I implied earlier, every time you add a new connection to the NVMe over Fabrics target, it is pinned to a specific core, a specific thread actually, and that allows us to locklessly submit I/O. So we don't have to take any locks in the I/O path at all. We've actually extended that same concept to handling more involved admin commands. For example, formatting namespaces and things like that. We also don't take locks when modifying the shared controller subsystem data for an NVMe over Fabrics target controller. What we do instead is when we receive one of those I/O, we actually pass messages from core to core to change that shared state, and then resume I/O after it's done. So we're completely lockless there, and we're 100% pulled. All right. So I'm going to jump into a few of the improvements we've made in the last year since the previous summit related to the RDMA transport. So one of the biggest ones that you'll see affecting you if you're a user of the target is shared receive queue support. Now, to give you a little bit of background, when you're working with RDMA, you have for each one of your queues, you actually have 3 separate queues. One in which you submit receive operations, send operations, and then you have a completion queue that you process completions for both of those types of operations. In the most basic case, one completion queue is responsible for a single submission queue and receive queue. Now in SPDK, since we pull all connections for a specific, all connections that are on a specific core, we've actually had the shared completion queue implemented since the beginning of the transport. And what that means is all the submission queue completions and receive queue completions for every single queue associated with a device are pulled on the same completion queue. And that allows us to save some resources. In the last year, some of the contributors from the community have submitted patches to actually share the receive queue between all of the connections as well. And that's pretty significant from a memory perspective because it allows you to disaggregate all of the requests and buffers from a specific queue pair, and you actually share that pool between every connection on the core. Since you know the size of the receive queue at startup, it allows you to allocate all of those buffers and requests at the beginning of time, so you don't have to worry about making those allocations at runtime. It makes scaling connections much cheaper while still allowing you to have the same burst I/O depth for a specific connection. The one drawback is it can increase the cost of core scaling. Now this shared receive queue feature is a hardware feature, so we actually have support for both shared receive queue devices and devices that don't support that. So the memory hierarchy here looks a little bit different for both of those. And if you're working with your RDMA target, you'll want to maybe turn on debug mode the first time you start it up to make sure your device does or does not support shared receive queue, because it's going to influence the way you allocate memory throughout the life cycle of your application. So if you have a network device that does support shared receive queue, all of that is going to be stored in, we call it a polar object, which is what gets pulled on the core per device. And it's going to have all of your receives, requests, and in-capsule data buffers stored in that polar. And as you add queue pairs, there's just a small queue pair structure that gets added for each queue pair that's just a few hundred bytes to store some state information. And then, of course, you have one of these polars per thread that's going to have all of the resources allocated to it. When you have a device without shared receive queue support, you're going to have all of those receives, requests, and in-capsule data buffers stored up in the queue pair. So every time you allocate one of those, you're going to have to allocate all of that memory. So just to give you an idea of what this looks like, on the left, I have a situation where you're keeping the number of cores constant, but continually adding new queue pairs. So as you can see on the shared receive queue side, you're basically pinned. But as this goes up, you can increase quite quickly. So I crunched a couple of numbers. I'm just going to look at them down here. If you use the default queue pair size, 128 for the queue depth, 4K in capsule data, you can add up to 700 kilobytes per queue pair of data. So this line actually goes up pretty quickly when you're looking at it. And now on the right side, I've got the scenario where you might have a very limited number of queue pairs, and that stays constant as you scale the number of cores. For the shared receive queue, that obviously is going to increase very quickly as you add cores. So it's important to know before you start up your target how many connections you might expect to have and scale your submission queue size accordingly. Okay. I want to talk about a few more of the improvements that that have already been completed or are coming. So for increased kernel interoperability, we've added support for the send with invalidate command. We've also added multi-scatter gather element support in both our target and initiator. So that allows, previously what we were doing is if you had a scatter gather list on the initiator side, that actually had to be split into multiple NVMe over Fabrics requests before it was sent over to the target. But this allows you to have a scattered list on the initiator that can be sent over as a single request and processed on the target. Excuse me. Sorry. Something we're working on right now is increasing the number of NICs that we support and test against in our test pool. It includes NICs from vendors like Mellanox, Intel, Chelsea-O. Something we're really excited about on the performance side of things is batching send and receive operations. So every time you submit a send or a receive, or you post a send or receive to the NIC, you have to call down into that stack and actually perform an MMIO write. So we hope that as we pull all the connections on a single thread, we can batch all the posts that we need to do and submit those one time in order to save quite a bit of software processing bandwidth. I don't have any official numbers on this. Jonathan Richardson is a community member who had posted some performance questions on a GitHub issue recently, and I directed him to this patch, and he said he got about a 4% improvement in his 4K workload that he was running. So pretty excited about this. We're still got a lot of testing to see how it's going to pan out. Another thing that we've been working on, you actually have an engineer in Poland, Karl LATENCY, who's been working on automating a lot of the performance tests that you've probably seen online that were originally run by Vishal Verma. And we're excited about this opportunity because it allows us to check at regular intervals for regressions in performance and kind of nip those in the bud before they become a bigger problem, before they end up coming into a release. It also allows us to track all the improvements that we're making and kind of just keep ourselves continually focused on improving performance. Some of the things we're in kind of earlier pathfinding stages for are supporting the extended verbs interface, which allows more granular configurations of things like completion queues. And if you were here yesterday, you saw a great talk from Oren and Sasha from Mellanox about NVMe over Fabrics target offload support, which will make SPDK more configurable to do support offload in, for an SoC or a smart NIC, something like that. So you can free up some more of those Xeon cores to do more meaningful or profitable work. So we're really excited about what's coming in the NVMe over Fabrics RDMA transport. But the biggest achievement and change to our target this year is the addition of the TCP transport. So I'm turned over to Ziye to discuss that with you.
Thank you. Yeah, thank you. Thanks, Seth. So it is my time to introduce the NVMe TCP transport development status in SPDK. As is well known, the NVMe TCP transport specification, named as Technical Proposal 8000, was released in November last year. And at the same time, both the developer in kernel and SPDK announced support for the NVMe TCP transport. So currently, we can see that in SPDK, we have several transport supports. And for the Fabric channel support, the patch is submitted by Broadcom and NetApp. It's still in review process. And for the TCP transport, it is already merged in 1901 in SPDK. And to make it flexible, we support different socket APIs, like the project support named as kernel TCP stack. And also we can integrate VPP. For here, I mark the VPP support is in progress. The question is that SPDK can already integrate it, but there are some stability of VPP. We still need to tune the performance and also may use the new version VPP to do some further testing. Also, you can find the many TCP transport support for both initiator side and the target side in these folders. So for the general design and implementation of many TCP transport in SPDK, it can be concluded into 4 scopes. The first is that we still follow the general design principle of many over fabric target. For example, we still use the polling groups in each CPU core to handle all the connections. And also, we use the shared buffer to share the buffers among different polling groups on multiple CPU cores. Definitely, this will save the footprint. Although there still are some contention for the shared buffer, but for each polling group, we will reserve some buffers at the beginning for the polling group. So according to our test, the contention for the memory resource can be ignored. I mean, for the performance respective. The second is that we reserve the interface to optimize the TCP connection. As mentioned before, we can use different socket APIs. Currently, we can support POSIX and VPP, but if you want to integrate others, like TCP, FStack, or SISTA, or others, you can implement it according to the socket API defined in SPDK. You implement the related function, then you can easily support that. The third scope is about the many TCP PDU handling. For here, we follow the spec to use the state machine to track all the status. And the fourth is about the many TCP request life cycle handling. We also use the state machine to track it. More details can be seen in the following page. So here, you can see there are 5 states to track the many TCP PDU. We name it as the ready state, to wait for the common header, to wait for the PDU specific header, and also to wait for the payload. And another is the arrow state. This exactly follows the specification defined by MN Express. So I will not pay too attention here. I think the most important thing is that besides following the spec, we define lots of states for many TCP request handling. Maybe there are too many states, but this is for the programmer to understand the code. Here in the loon, you can just view that. I think the most important thing is for this state transition diagram. With this state transition diagram, you can easily understand the code. If you can understand the state transition machine, I think that the code is exactly the same. So let me have some brief introduction. The first is that we have a bunch of many TCP request states defined. And the first is the free state. When we receive the command capsule PDU from the initiator, we will mark the request. Sorry. We can mark the request as a new request. And if this command doesn't need any buffer, it means it is neither a read command or write command. Then we can directly send it to the user space to execute this state, and the three states are used to track the many TCP request state in user space driver. So you can, I mean that it can be grouped into one. And if the command is a read or write command, we definitely need a buffer. Since we mentioned we use the shared buffer mechanism, so we need to allocate a buffer from the shared pool. And if it's a read command, we just read the data and fill the command from the initiator, and finally compose the. Sorry, I mean that if this is the write command without need to send the R2D command, we just receive the PDU data from the initiator side and compose many command and directly send the user space driver to execute. And if it is a write command, we know that according to the definition of the write support, we need to send the R2T to the initiator. Then we will need to wait for the wait a status to wait for the R2T slot. Since we know that in the protocol there are restrictions for the R2T numbers. So if it can allocate the R2T slot, then we send the R2T PDU to the initiator, and finally we receive the data from the initiator and then compose the MVNE request and send it to the user space MVNE driver to execute. And finally, after the MVNE command is synchronous executed, then we can send the response PDU. It can be the MVNE command response PDU to the initiator. Or if it is a read command, we need to send the controller to host data to the initiator. And finally, the request can be completed, and we just free it. So this is all the life cycle tracking. If you want to further develop your own MVNE over Fabric target based on SPDK, I think it is very useful for you to understand the code. And here we show some performance data. I think most of the audience care about the performance. And in this test experiment, we used 3 machines which are directly connected without the switches. 1 used as a target and 2 as the initiator. And in the target site, we use 16 Intel P4600 MVNE, and we created 16 subsystems. And each subsystem is equipped with 1 MVNE SSD encapsulated as MVNE BDEF. And these 2 diagrams shows the I/O scaling on the target side. We choose 2 typical workloads. The first is 4K random workloads with 7% read and 30% write, and the queue depth equals to 1. And the second is the queue depth equals to 32. From the second diagram, you can see that if we configure different CPU cores for the MNUR fabric target from 1 to 4, we can see the performance number can nearly linear increase from core 1 to use one core to 3 cores, but there are slight decrease from core 3 to core 4. It means that there are slight performance drop, not linear. But the trend you can see that the performance can be increased. And also for the latency, if we handle the same number of connections, if we use more CPU cores, then we can see that the latency can linearly decrease with this trend. But from the first diagram, you can see if we just use QDEPS equals to 1, the performance increment of the IOPS or the decrement of latency is not quite obvious. The reason is that if you use a QDEPS equals 1, there is the asynchronous execution can be nearly concluded as a sync execution. So it is not very clear here. And this diagram also shows the same I/O scaling with using SPDK initiator on the initiator side. So I will not pay too much attention here. And the most interesting thing is we test the end-to-end latency using different targets or different initiator. And in this test, the non-BDEF is used. For the kernel, it can also use non-BDEF. And the first diagram shows the average latency comparisons between SPDK target, but we still use the kernel initiator. It means that we use the kernel target and the kernel initiator as the baseline. In the first diagram, we replace the SP target with the kernel target. Then we can see the total latency for 3 typical workloads. The SPDK's latency is improved about, the average is 20% on the target side. And then we do the second test. The second test is we use the SPDK target on the target side. It means that the second experiment is to continue replace the kernel initiator with the SPDK initiator. And from this test, we can see from the initiator, we also have about 20 to 30% latency improvement. So if we convert the 2 diagrams into 1, we can inform a third diagram. In this diagram, it means the average end-to-end latency comparison between the kernel solution. It means that for each solution, for example, for the kernel solution, we use the kernel target on the target side and the kernel initiator in the initiator side. So finally, we can compare the performance difference. We can see that according to the diagram, for each workload among the 3 ones, the average latency improvement can be, the number is about 40%. So this diagram, as mentioned, we use the non-BDEF. So it states that if we just test the network latency, use both the kernel TCP stack, SPDK performs about 40% latency improvement. And let's see the IOPS, per-core IOPS comparison between SPDK and the kernel on the target side. In this experiment, we still use the 16 subsystem, and the SPDK is configured with 4 CPU cores. And to achieve the same or similar performance, the kernel uses 9 to 12 CPU cores. So we just calculate the per-core CPU, per-core IOPS in the target site. We can see that using the 3 different workloads, we can see SPDK target is about 2.4 times the kernel target on average. So definitely we think that using SPDK-based user space and many TCP solution will be much better than kernel.
I have a question. Why the latency difference and IOPS difference are not linear? So here you show the IOPS difference is 100%.
Yeah.
The latency is about 20%.
Yeah. Actually, the latency is the abstract, absolute value. But for this, the improvement is the per-core IOPS. It means that if you have the same hardware, actually you can achieve the same performance if you add more CPUs to saturate the hardware. For example, saturate a network or the SSDs. But in this test, we just want to compare the per-core performance. It means that the SPDK can use less CPU resource. So this will have great benefit in hyper-converged infrastructure. It means that in this infrastructure, you can sell vCPUs, but you still want to use CPUs to handle the IOs. So if less CPU resources are used to handle the IOs, then there will be more CPUs can be leveraged by the cloud providers to provision the vCPU service, like VNs or others. So this page shows some further development plan. We still want to enhance the functionality, and the second is to continue the performance tuning, and the third is that we want to continue integrity with third-party TCP stack like VPP or others. And the fourth is that we want to leverage hardware features. For example, for Intel's CVL, I mean the Columbia Wire Park, 100 gigabit NIC, we can definitely use the ADQ features or others to do the further optimization. For Marox network NIC card, we can use the Marox message accelerator library for acceleration. And the fourth is that we know that there are still a lot of work to do the offloading through smart NIC. So we also want to do some optimization in the future. But for this, according to my knowledge, we definitely need a new specification, maybe discussed or defined by MM Express later. Then we can have a standard to do the offload. So this is my part. So let's just to do the conclusion for this talk. Thank you.
Great. So today just to recap, we did a little walkthrough of the improvements that have been made to the RDMA transport, and Ziye, who actually wrote the TCP transport, walked us through the development of that transport and gave us the performance enhancements for that. As we both mentioned, there's still so much we can do on both the TCP and the RDMA transport. And we hope that as a community, we already have great community involvement in developing these features, but I know that as we continue to get more and more involvement from the community, we can make these pieces of software really, really fast and really, really efficient. So Thank you all. I'd like to open it up for questions now. Anybody has them? Yes, we'll have Nate will bring the mic down up here in the front. In the front, yep.
So have you done the performance comparison between RDMA and TCP transports? And also, have you done the large-scale scalability testing with the TCP? We know that RDMA that's the question for the scale, but TCP is supposed to be much, much better. So two things, the performance and also the scalability.
So I don't have a direct comparison between the RDMA transport and the TCP
Actually,
transport.
I have sent the diagrams in the backup page.
Oh, great. So he's one step ahead of me.
Yeah.
I was just about to say we do have,
Yeah.
I'll let you go there.
Yeah.
We've run the same performance tests on both the RDMA and TCP transport, so you could make those comparisons, but it looks like Ziye's already put those graphs together.
So this is a very simple comparison user Mallox cut. We can see from the diagram, we can see that the first line is the RDMA latency. The second is the TCP kernel stack, and the third is the TCP with using Mallox offloading library. You can see that normally it is clear that the latency of the TCP compared to RDMA is about maybe the latency can double. It means that it may be 2 to 4 times. I mean the latency increase, and if you use the offloading, it can be solved with some latency improvement. And also for the IOPS, normally TCP transport is about, the IOPS is about 1/7 about the RDMA transport. It is the expected value, but if you're using the TCP, using some offloading, the IOPS can be improved. And also for the throughput, we didn't do the too many experiments. But finally, for the throughput, for both RDMA transport and the TCP can saturate the NIC. So this is the conclusion. So and though we do the experiments using the Mallox cut, but we can have the similar result on Intel's NIC cards. So I just put it in the backup page, since it is the very early experiments. We still need to confirm that.
Great, thank you. Any other questions? We got one from Sasha.
So Sasha from Mellanox. So we also work on NVMe Fabric TCP solution. We also analyze performance of VMA in SPDK, and we see some direction for improvement. In our internal, I can't share any result, but in our testing, VMA overperforms VPP, and and we also see some directions for improving in VMA solution. And about RDMA solution, so we're planning to push some improvements for RDMA for NVMe Fabric RDMA. So there is room for improvements in this area.
Thank you.
This is not a question, right?
Any other questions? Okay. Any CPU usage comparison between TCP and RDMA?
Actually, you know that currently for SPDK, we all use the fixed CPU cores to start. So we know that yesterday, Ben Walker talked some optimization about the reactor mode or the threading mode in SPDK. But here, You mean the compare the CPU core utilization for IDMA and the TCP. Actually, we still use the fixed core numbers. So actually, from the users, if you start one CPU cores to do the RDMA transport, you can also use the one CPU core to do the TCP transport. But it means that you can see the performance of the TCP for the IOPS. It is about, as I mentioned, 1/7 or 1/6 of the RDMA transport. So it means that if you want to achieve much better performance, you need to add more CPUs according to this usage. Yeah, this is my understanding.
Is it a purely CPU powered or is it just transport?
Hold on, sorry.
One sec.
So for the TCP transport, you're saying is purely, the core bounded, which means if you add more cores, then you can match up to the RDMA performance.
Actually, I think that it will be nearly a same result for the RDMA transfer. It means that if you're using more for TCP transport, if you're using more CPU cores, there are more improvement for the latency. Since I think the major cost is for the system cost, for example, to leverage the TCP kernel stack. So this is the bottleneck. But for RDMA, if you're using more CPU cores, I don't think there are too much improvement for the RDMA transport on latency. It means that I don't think there are too many interactions with the kernel on RDMA transport.
No, I guess my question is that if you use one core for the RDMA, can you use, you said the performance IOPS is 1/6, of the, is 6 times of the TCP, but if you give 6 cores to the TCP, would you match up to the same IOPS compared to the RDMA? Or as you said, it's really just the TCP kernel stack is the bottleneck.
I think you may not easily compare this. Yeah.
Should we go back here? Because we're getting about 1.2 million IOPS per core on 4K random reads with RDMA. Let me go forward to his numbers specifically on the TCP transport. Yeah, so it looks like you're starting to approach that when you get to 4 cores with 32 Q depth on the TCP transport. You're hitting about 812K. So I mean, it's definitely quite a big trade-off, right?
Yeah, according to our experiment in the same machine, if you're using 4 cores for RDMA transport, we can achieve about 2.6 million IOPS. But here, you can only achieve 0.8 million IOPS. If you're using the local MNE SSDs, we can achieve about 4 million. So I think that we do not directly have a very compressive experiment for this. But it seems that for the same CPU resources, maybe we can have a conclusion. Maybe, we still need some more experiments. It is about the 1/4 or 5th to 1/6 performance IOPS degradation between the between the RDMA and the TCP transport. This is only compare the kernel TCP transport. Yeah.
So were you at 100% CPU utilization on all 4 CPUs at this point?
Well,
Repeat the question.
Oh yeah, sorry. So the question was, were we at 100% core utilization on all 4 of them? Well, it's SPDK, right? So we're always polling, right? Every single one of your cores.
So this is why Ben Walker yesterday talked about the threading mode of the scheduler. he wants to exactly calculate the CPU resources. From now on, if you use the system tools to track the CPU utilization for SPDK application, it will always be 100%. But we know that for some percentage, it is sleep state.
Yeah, and so, I mean, for this one, we know that we're CPU bound, right? Because as you increase the number of cores, it's going up. So you can be fairly certain that on every single poll that you go through, you're going to be reaping new I/O. So I would say that, even from an SPDK perspective, you're pretty full up on all of these cores when you're running this benchmark.
But it's a fair question. I don't know if you were in the talk yesterday about the threading model changes. Over time, that the answer to that question will change with that.
Yeah, there will be a lot more information we can glean from the poller, so you're right. Yeah.
The potential of this, CPU bounded stuff is that we move it. I just want to add your comment. If this is the CPU bounded, then it could be a problem when you move this to the smart NIC, because there you really don't have that luxury of more cores.
Yeah, I think it's a much more complicated conversation, though. I hear what you're saying.
Great.
I'm looking to your one core number. So what's the maximum frequency? I mean, when you have turbo enabled, I couldn't find the speed here in your configuration information. Is it 4 gigahertz or is it higher? Like, what's the maximum speed when you have turbo enabled?
Do you know the turbo frequency here?
Basically, I'm trying to find out how many cycles you need for one IOPS in the one core number.
Oh, I don't know the turbo frequency off the top of my head. These slides are going to be posted, though.
Okay, good, awesome.
And I'm sure it's somewhere in that, that stuff down there. I think are we just about out of time? All right, we'll give you guys time to get to your next.
All right, thanks
next talk.
everybody.
Thank you.
Good job.